Hello everyone, welcome. Today we'll discuss a recent paper called Universal Paralinguistic Speech Representations using Self-Supervised Conformers. This paper is coming from Google Research. The tutorial overview is as follows. First we'll see the introduction of the paper. Then we'll see the conformer-based representations, how they are generated and how they are used. Then we'll see the experimentations and finally we'll see some results. What is paralinguistics of speech? In simple words, paralinguistics of speech is just the attributes of the speech signal. What are the attributes? For example, when somebody speaks something, they can express a lot of things, or the speech contains many informations. One simple information is the speech or the text itself, and others include emotion, speaker identity, and so on, right? Or the gender information and so on. So these are called paralinguistics of speech. And we already seen in the recent days that building a large self-supervised model using a model such as Wave2Vec on clean speech data, you can get very good speech recognition models accuracy. And can we do the same thing for non-speech signal? So what are non-speech signal? Not exactly non-speech signals. So can we do it for paralinguistics of speech, such as I said, predicting emotions, gender, and attributes such as emotion, gender, and speaker identity, and so on. Right. Now, this paper proposes to build a large-scale self-supervised or conformer-based self-supervised model, and then we can fine-tune that large model, or we can use the features from that large self-supervised model for downstream applications to detect these paralinguistics of speech signal. And the model is built using enormous amount of speech data, and the scale, the model size itself is over 600 million parameters. And this paper shows that building such a huge building such a huge self-supervised pre-trained model and then fine-tuning can give you very good performance on these paralinguistics tasks. And we will see the results and the model architecture and the data used for training and so on in the coming slide. And they also ask a question: can we build a single universal feature extractor for all the speech tasks? And we can see the answer in the coming slides. So what are these conformer-based representations? Before looking at this slide, let's look at this slide, from which we will get some idea of what kind of models, and what is the data set, and what are the architectures and parameters, number of parameters, and so on. Let's just see these. There are many architectures have been proposed in the past, and most of them are from Google itself. Like for example, Trill is from Google, and Frill is basically a student or a distilled version of Frill. And we have this Cola model, which is sort of a, we'll come to what this model is in the coming slide. But and can we use ASR embeddings directly? Like if you have a production level ASR model, can we just take the embeddings from the last layer of the ASR model, and then can we use it for these applications, right? And the model architectures, as you can see here, there's this MobileNet, and here Trill uses ResNet Dish 50 and MobileNet V3 and so on. And then we have RNNT here, and number of parameters, as you can see here, they are little small because they are trained on small data, and the training data is the audio set data, right? And this column says whether they used the labeled the labels or not, right? Now coming to this paper's idea, or using this conformer based large self-supervised model, which looks like a Wave2Vec. The architecture is again conformer, because it uses conformer layers in the feature extractor, not in the feature extractor, in the context network. And if you just see this conformer Excel, which has no relative attention, but trained with huge amount of YouTube data, which is approximately 1 million hours of YouTube data. The model size is 608 million parameters, and that is just one model, and the labels are not used, right? And similarly, they have conformer XSL, which is 1 billion parameter model trained with again YouTube data and the LibriVox data, right? And again, no labels are used. And similarly, they have conformer G. I think it is G for gigantic or something. And they have like the model size is 8 billion, right? So now that we have seen three different new models, which are these conformer XL, XSL, and G, let's go back and see like how those models are trained. And for training, they are adopting the wave-to-wake type of architecture, where there is a feature extractor which takes a raw audio as input, and the feature extractor will have one-dimensional convolution layers with some downsampling, and the convolution layer takes one-dimensional raw audio and extract sequence of feature vectors. And sorry about the previous sentence. So the conformer takes that does not take the feature encoder does not take raw audio. In the old wave-to-wake idea, it takes raw audio, but in case of this paper, they use MEL filter banks or log MEL spectrogram features. But the feature extractor itself is a 1D feature extractor which has three layers, right? 1D convolution layers, three of them, and it takes 80, 80 features at every frame, and those features are log MEL spectrogram features, right? So that is the feature encoder, and then the output of feature encoder goes to the context network, which will have many conformer layers, right? And the output along with the quantized representations are used for computing the wave-to-wake loss, which is the contrastive loss, right? So that is the wave-to-wake 2.0 style loss, which is used for training here. Now, like if you want to know more about Wave2Wave 2.0, I already have a tutorial in my YouTube channel. You can check it out. And the conformer encoder, like I said, there are multiple of them. One which has 608 million parameters has 24 layers of conformer blocks and 8 attention heads in each block, and the feature dimension, the output dimension is 1024 units. Similarly, there is 1 billion parameter model, which has 42 layers and 8 heads in every layer. And there is another conformer G model, which is 8 billion parameter model, which has 36 layer, less than 1 billion, parameter model, but it has more number of heads in each layer. And the output dimension also is 3 times that of the other two models. Now, like I said, for training, they are using around 1 million hours of audio data extracted from YouTube. Specifically, it is like exactly it's 900 hours of our data set, 900 hours of audio extracted from YouTube. And the way the data set is built is they just crawl 3 million hours of audio from YouTube videos, and they just remove all the non-speech part by running running audios through speech non-speech detectors, and then only if they only use the speech part, they get around 900 hours of unlabeled audio data, which you can use it to train or to pre-train these heavy conformer models, right? And the second data set they're using is the LibriLite, which is around 60,000 hours of audio data, which is clean studio recorded audio data, audio books actually. So this 60,000 hours of audio is also used for pre-training the models, the large self-supervised models. Now that we have seen these two, the conformer based feature representation, so you already know like how the fine tuning works is that you just freeze the conformer model, or both the feature extractor and the conformer model. Then you use the context features, or you just feed any audio and extract the top level features, or it can be any other layers of features, and then feed those feature vectors, or you can simply aggregate all the features and create a single feature vector, and you can simply use a linear classifier to classify that into classify that into any task you are building, right? So for example, they're using 9 different tasks here, 9 different uh, you can think of them as problems, right? They are solving 9 different problems using the single model, and these are the paralinguistic tasks, right? So there is one. So first we'll look at the data set they are using for fine tuning, and like the target, what is the target, and what are the number of classes, and how many data, how many samples they have for training, and the length of the audios and so on, right? So there are 9 different data sets here. One is this voxelab. Obviously, if you are in speaker recognition or speaker verification field, you will know about this voxelab data. And it's mostly used for speaker identification task. And there are 1,200 classes, means there are 1,200 speakers, right? Pretty big data set. There is a VoxForge data, which people use for both speech recognition and other tasks like accent ID and so on. But there is you do something called language identification from this data set, and there are 6 languages, and the data set length is like this. And you have commands, speech command data set, which is kind of a classification data set. You have commands like 10, 12, or 36 commands, and each command has so many examples. And in this case, they are using only 12 classes. And given an audio, you just have to classify that particular 1 second worth of audio into one of these 12 classes, right? And you have masked speech. So this is basically a new problem. So since now, because of Corona or COVID, many people are wearing masks, right? So speech attributes changes when you speak with mask and without mask, right? So the problem here is if you have so the problem here is to detect whether you are wearing the mask or not by listening to the audio, right? So it's just binary classification. So let's say you're given audio, you have to tell. Humans can pretty easily tell if you're talking with mask or without mask, but can we train a model to do the same thing? So that is the question they're asking, right? So that's called the masked speech problem, and the target is mask wearing, whether wearing or not, and so many examples, and the duration is 1 second, the average duration. Then there is a task called ASP spoof, which is basically detecting whether the audio is synthetic audio, or it's a real audio from for example, recorded audio, right? So recorded in a sense like the human recorded audio. So the task is to identify, given an audio, is it generated or synthesized using some algorithms such as TTS or voice conversion, or if it is real audio recorded by a human, right? So that is the task of this ASP spoof, and it's a binary task. You just have to detect whether it's bona fide or synthesized and so on. And the data set is a ASP spoof data set. And you have Euphonia, which is also it's also another data set released by Google. So the idea here is to detect whether the audio is deserted. Uh, it's a so basically, when some people so there is this problem called detecting dysertric speech, right? So basically, if there are if people are suffering with some sort of speaking problems, so you can identify by listening to them, right? So there are many many people who suffer from this speaking problem, and so the idea is to detect whether the audio is as contains dysarthria or dyserthritic or not, right? So there are 5 different classes. So basically it measures the intelligibility of the voice, not exactly the intelligibility, but sort of a like whether the audio is kind of problematic, or not, right? So I don't know how to put it, but it's just that I mean the whole idea is very simple. uh, is it like normal audio, or if it has some sort of problems while while speaking. So that is the idea of this paper, or this euphonia problem, right? And there are 5 different classes. So if you give an audio signal, you can classify that audio into 5 different levels. And that tells you the audio is disorder coming from a disordered speech, or if it is it's a clean speech, right? So that is the phonia problem. And Kinemati is emotion. IMOCAP we already know. I think many people will know about the emotion IMOCAP dataset, and SAVI is also emotion dataset. 6 classes for Kinemati, and IMOCAP has 4 classes, and SAVI has 7 classes, right? So now that we know the datasets now, and we also know like what they do, right? So what they do is, given these datasets, for every dataset, you can simply take the dataset and extract these features, and then fine tune them, or you train a linear classifier on top of those extracted features, and then you can report accuracy results, or error numbers with those for those data sets. Now, before we go and see the results of this model, or this paper, let's look at like the previous state-of-the-art results, and also some of the baselines they are providing here, right? So the previous state-of-the-art, for VoxLab, they don't have any, they haven't mentioned any, and for VoxForge, they have 97%, 95.4% accuracy for the language identification task. We have 97.9% accuracy for speech command, which is the command classification task. Then they have 73% state-of-the-art accuracy, and for ASP spoof they have 11. This is actually error rate, ER. So lower the better. So, and for euphonia, it's again classification problems. It's accuracy, so higher the better. And then you have CREMA-D and IMOCAP and SAVI. So since I work in emotion recognition field, I work in speech field basically. So I have some papers in emotion, specifically with these IMOCAP datasets. So I have seen like recent studies on this IMOCAP dataset. So the state of the art is actually not 67; it's more than 76, because there was a paper in Interspeech last year, which is 2021, from Baidu Research, which mentioned an accuracy of 76 point or 77 percent accuracy on IMOCAP dataset, using something called multimodal um, emotion recognition, using the Hubert, or these high level, or these pre-trained huge pre-trained self-supervised models, right? And I think this number they are showing from the superb challenge paper, but I feel the real state of the art is the Baidu's paper. But anyway, that this model is anyway still beating that, both of them, both of the models. So 79.2 is the state of the art accuracy. Before coming here, let's understand like the state of the art and the data sets and the baselines. So Savvy is again 84% previous state of the art, right? And they have baselines with many models. So as a matter of fact, most of them are coming from, I think all of them are coming from Google Research only. So Drill, Frill, Cola. So this Cola is basically is a very interesting idea, which is not exactly self-supervised idea, or it is a self-supervised model, but not trained like not trained with contrastive loss. It's trained with sort of a um, the two-way network idea, or not two-way network. Uh, um, I just forgot the model name. Um, anyway, so the Scola is basically, so the idea is very simple. So given an audio, right, you can simply consider replications of the two models, and then extract high level feature and then compare, right? So with some different laws, or Euclidean distance laws and so on. But even with those, you are already getting a good self-supervised models, right? So so that is cool. And ASR embedding is just the embedding, last layer embedding extracted directly from the speech recognition, production level speech recognition model. right? So that is the ASR embedding baseline. And with this baseline, let's look at the conformer's accuracy. So as you can see, the state of the art is obtained with this conformer model, but not by a single model. So what they are doing right now is they are selecting model out of 3 models, which are basically Excel, conformer Excel, which is a 608 million parameter model, and there is a XXL, which is 1 billion parameter model, and there is G or conformer G, which is 8 trillion, sorry, 8 billion, sorry, not really, 8 billion model parameter, right? Sorry, 8 billion, 8 billion parameter model, right? And so what they're doing is they're just training all the 3 models, and they're fine tuning all the layers, and they're just taking the best of those combinations, right? So which model, which layer, right? So whichever works better is just taking and providing the accuracy here. So as you can see in this column, um, they have the accuracy number, which is basically here they have the best. Uh, I think this is a mistake, I believe, because so Voxelab, this was not supposed to be. I think okay, this is this. I think this is speaker. If it is speaker verification, I mean, if it is EER, it should be lower. If it is accuracy, it should be higher. So I believe this is accuracy, because as you can see, the trend is going down here, which means I okay, trend is going up, right? So okay, but only for the ASI embedding it is slow. So I believe this is accuracy. So they are like getting very good accuracy, the speech recognition, speaker recognition accuracy. I believe it's not EER. If it is EER, it should be lower, right? Anyway, and they have for Vox4, it's a language identification plus language identification task, which is basically the accuracy. So accuracy should be higher. As you can see, you are getting almost 100% accuracy, which is great. And then you have speech command data set, and for that you're getting 97% accuracy. So as you can see in this case, XXL which is the 1 billion parameter model, at layer 25, if you fine tune, you will get best accuracy. And in this case, if you fine tune the 8 billion parameter model at layer 19, you will get the best accuracy. For this, you have to use something called conformer aggregated, I forgot what piece, I think projection, I believe. So if you use that model, then you get the state of the art accuracy. So sorry, conformer applied to paralinguistics is called CAP. So that model gives you 97% 5.5, and still not beating the previous state of the art. But anyway, if you fine tune at layer 16, you will get 97.5. But the state of the art is still the previous model. And for mask speech, you have to use the Excel, which is I think the 608 million parameter model, which has no relative attentions, and fine-tuned with both YT and YouTube data and LibriVox data. And you have for ASP spoof, you are getting 2.5% accuracy, 2.5% EER, which is very good. And that model, the best model for that task is the CAP model, conformer applied to paralinguistics model at layer 12. And then you have Ephonia, for that you are getting 53.6%, which is not as good as the previous model, the ASR embedding model here. Um, so so similarly, for the IMOCAP, as I described before, you are getting 79, which is this is the state of the art accuracy, because I haven't seen any paper which shows this high accuracy. And for Crema-D again, you have they're using the conformer G model with fine-tuned at 26 the layer, and so on, right? Now you can also ask a question, okay, what if I want a single model? And so for that, what they're doing is they're aggregating features from all the models, and then they're fine-tuning for different layers. So that is the last one. But for so you can ask a question like, I don't want to use, like, I don't want to report results on many models. I mean, I don't want to fine tune with many models and then choose the model. So they are using this CAP model, which is the conformer 608 million parameter model, and they can vary. They can train the for each task at different layers, and they are getting this much accuracy. And you can also ask a question, okay, what if I want to build a universal model and universal feature extraction, or universal or the layer which I want to extract from a single layer, not from, I don't want to try it on all the layers. I want to try it with all the layers. So I just want to know, okay, which layer is the best for all the tasks, right? On which model, right? So for that, they have done experiments and they show that with CAP12, which is the 608 million parameter model at layer 12, is basically the best. Not the best, is like a reasonable compared to any other layers, right? So this is the result section, and coming to some of the other experiments they have done. There is they have done experiments with varying lengths of audio. So basically, you can take uh, different durations like chunks and then pull features from them, right? And then aggregate all the features across all the segments and then fine tune, right? And if you do that, as you can see, um, the accuracy changes here from different segments, and then also check against the conformer layers, right? So that is one. And some of these bars, like they are the previous baselines, and how much percentage of accuracy you will lose if you use uh, so much durations of the segments, right? So that is also another experimentation you can do. If you use very small segment, you will lose lots of accuracy. If you use larger segments, you won't lose much accuracy. And they have done it for all the tasks. And that's all for this tutorial. Hope you guys learned something today, and hope you enjoyed the video. Thank you so much for watching. See you guys in the next tutorial.